Lubricating oil, an invisible hero that sustains the performance of machines. But what if the long-accepted norm of more is better lubrication is actually causing heat buildup and vibration? We questioned this conventional wisdom and returned to the fundamentals. What we discovered was a new idea: deliver only the minimum required amount, precisely where it's needed. This is the concept behind nanoliter lubrication. With zero mist emissions, it's an environmentally friendly solution that achieves quieter, more efficient rotation than ever before. Let us introduce you to the next generation of lubrication technology. Here's what we'll be covering. Using an angular contact ball bearing as an example, we'll explore the true essence of lubrication. First, where exactly should lubrication be applied? Understanding this point is the critical first step. Next, we'll uncover the sources of friction inside the bearing: rolling friction and sliding friction. How we minimize both determines overall performance. Then we'll address a major challenge in high-speed bearings: the invisible air barrier that prevents lubricant from reaching where it's needed. To overcome this, we developed a new approach: nanoliter lubrication. This technology delivers incredibly small amounts of lubricant with precision, exactly where it's needed. And finally, we'll share why reducing lubricant volume is not only possible, it's essential for both performance and sustainability. In the left diagram, the blue lines show the rolling contact paths where the balls rotate along the inner and outer raceways. These paths are the only locations that require lubrication. Other steel surfaces do not need to be lubricated. In the right diagram, the red area shows where the ball slides inside the cage pocket. This is another site that requires lubrication. So in summary, only two areas need oil: the rolling contact between the ball and raceways, in blue, and the sliding contact between the ball and cage, in red. Lubricating anything beyond these points is unnecessary and wasteful. This diagram shows where friction occurs inside an angular contact ball bearing. Both rolling and sliding friction are present at the contact points between the ball and other components. In the diagram, rolling friction is shown in blue, and sliding friction in red. Typically, the coefficient of rolling friction is very low, around 0.001 to 0.005. In contrast, the coefficient of sliding friction can be 100 times higher, sometimes even more than 0.1 to 1.0. Under certain conditions, sliding friction can become hundreds of times greater than rolling friction, causing heat, wear, and vibration. That's why it's absolutely critical to apply proper lubrication specifically to those areas where sliding friction occurs. Let's look at the air barrier problem in high-speed spindles. When a spindle rotates at high speed, an air barrier forms around the bearing. This air barrier repels incoming lubricant, preventing it from reaching the interior. In conventional oil-air lubrication, a small amount of oil is mixed with compressed air and sent toward the bearing. However, the air barrier significantly reduces the delivery efficiency of the oil. As a result, proper lubrication is often not achieved. Instead, oil droplets scatter, increasing environmental impact. Moreover, excess air and oil can generate frictional heat within the bearing, leading to rising temperatures and reduced bearing life. So how does nanoliter lubrication work? This innovative method dispenses an ultra-small amount of lubricant, just 10 to 90 nanoliters per shot, at fixed intervals. The droplet, held at the tip of the nozzle by surface tension, transfers to the moving surface without direct contact. This ensures a stable, uniform supply, just the right amount, exactly where it's needed. With this approach, lubricant waste and splatter are greatly reduced. And the system can be applied not only to bearings, but also to gears and other components. Our technology enables the nozzle to pierce through the air barrier created by high-speed rotation, delivering lubricant directly and precisely to the balls inside the bearing. The oil attaches to the ball and spreads uniformly across its surface through centrifugal force generated by the ball's rotation and revolution. It then lubricates the sliding contact between the ball and cage, and finally reaches the rolling contact between the ball and the raceway. This is how nanoliter lubrication delivers oil only to the essential points, without waste or oversupply, achieving the ideal form of lubrication. Only 4 components are needed to realize nanoliter lubrication. The nanopump unit, its controller, the tube that delivers lubricant, and the nozzle attached to the tube tip. That's it, no mist, no mess, no excess. In the next slide, we'll show you how this setup works inside an actual rotating spindle. Before we close, here's what we want you to remember. Global warming is progressing faster than we ever imagined. Extreme weather and large-scale natural disasters are becoming more frequent and severe. If we continue wasting energy and resources, the planet's future will become unsustainable. That's why we set out to drive meaningful change, starting from the often overlooked field of lubrication. By supplying oil with nanoliter-level precision, we can avoid overlubrication and reduce oil consumption by 90% or more. This innovation directly reduces co-emissions from oil production and disposal. It conserves petroleum resources and helps prevent pollution. It also improves mechanical efficiency and service life by reducing friction and energy loss, offering major economic benefits. Even better, it makes the work environment quieter, cleaner, and safer by eliminating oil mist. In short, nanoliter lubrication is more than a technological advancement. It's a small change that leads to a big transformation, benefiting the environment, the economy, and society. Now is the time to act. Together, we can help create a more sustainable future. Thank you very much for your attention.